sklearn, linear model, ElasticNetCV. Description: ElasticNetCV implements ElasticNet regression with automatic optimal hyperparameter selection using cross-validation. It combines the strengths of both ridge and lasso regression by penalizing both the L1 and L2 norms of the coefficients. This allows it to achieve sparsity like lasso while still mitigating the instability issues that arise from high correlations between features. ElasticNetCV searches for the best combination of L1 and L2 regularization strengths, L1 ratio and alpha across a predefined grid, using cross-validation to evaluate the model's performance. Inputs: XA2D array representing the training features. Each row represents a sample, and each column represents a feature. YA1D array containing the target values. Outputs: Coa the coefficients of the linear model. Intercept the intercept of the linear model. Alpha the optimal L1 regularization strength, alpha selected by cross-validation. L1 ratio the optimal L1 ratio selected by cross-validation. Steps: Preprocessing data is typically preprocessed before fitting the model. This may include scaling, normalization, or feature engineering. Hyperparameter tuning: ElasticNetCV searches through a grid of L1 ratio and alpha values to find the combination that minimizes the chosen metric, e.g., mean squared error on a held-out validation set. Model training: the ElasticNet model is fitted to the training data with the optimal hyperparameters determined through cross-validation. Metrics: mean squared error (MSE), a common metric used to assess the model's prediction accuracy. R-squared, a measure of the goodness of fit of the model, indicating how well the model explains the variance in the target variable. Visualization plots: feature importance plot, a plot showcasing the relative importance of each feature based on the magnitude of their corresponding coefficients. Residual plot, a plot of the difference between the predicted values and the actual values, allowing you to visualize the model's performance and potential heteroscedasticity. Fine-tune parameters: L1 ratio, the mixing parameter between L1 and L2 regularization. A value of 1 corresponds to lasso, while a value of 0 corresponds to ridge. Alpha, the regularization strength. Higher values induce more sparsity, more features set to 0. CV, the number of folds for cross-validation. Higher values lead to more robust hyperparameter selection but increase computation time. APES, the tolerance for the optimization algorithm. Uncertainty methods. Confidence intervals for the model's coefficients. Confidence intervals can be calculated using the bootstrap method. Prediction intervals can be obtained using methods like Bayesian regression, or by estimating the uncertainty in the predictions based on the data distribution and the models. Variance, challenges and fixes. Challenge 1: overfitting. If the regularization strength is too low, the model may overfit to the training data and perform poorly on unseen data. Sample use case: a model trained on a small dataset with a lot of features may overfit, leading to high variance and poor generalization. Fixes: increase the alpha parameter or use a larger dataset. Apply early stopping to prevent overfitting during training. Challenge 2: poor feature selection. If the L1 ratio is too low, the model may not effectively select the most relevant features, potentially leading to a less parsimonious and interpretable model. Sample use case: a model trained with a low L1 ratio may include features that contribute little to the prediction, making it harder to understand the model's behavior. Fixes: increase the L1 ratio to promote stronger feature selection. Experiment with different feature selection methods alongside ElasticNetCV. Challenge 3. Computational complexity. ElasticNetCV can be computationally expensive, especially with large datasets or high values of CV. Sample use case training ElasticNetCV with a large number of folds and features on a dataset with millions of samples can take a significant amount of time. Fixes: consider using a smaller number of folds or reducing the number of features. Utilize parallel computing or distributed training frameworks to accelerate the process. Challenge 4. Interpretability. Understanding the impact of individual features can be challenging, especially when the model selects a large number of features. Sample use case: it might be difficult to interpret the model's predictions if a significant number of features are used, making it hard to pinpoint the key drivers. Fixes: utilize feature importance plots or permutation feature importance to analyze the contributions of individual features. Consider using a more interpretable model, like a decision tree, if interpretability is paramount. Challenge 5. Dealing with multicollinearity. ElasticNet is known to be sensitive to multicollinearity, high correlations between features, which can lead to unstable coefficient estimates. Sample use case: a dataset with highly correlated features may result in coefficients that vary significantly with slight changes in the data. Fixes: regularization is the main technique for handling this, but consider addressing multicollinearity by removing highly correlated features or applying dimensionality reduction methods like PCA before fitting the model.